Welcome back! Okay, so now we get to talk about electric fields. What is an electric field? That is the topic of this video. Okay, so let's bring it back and talk about something that we are more familiar with. So we know about gravitational fields somewhat. We haven't talked about it extensively in class, but you have experience with it. So let's think. This is the Earth right here. So this blue hemisphere down here is the Earth. And let's consider a 1 kilogram block. So if the 1 kilogram block is close to the surface of the Earth, what force will that block feel from the Earth? Right, it'd be the weight of that block. The weight of the block is 10 newtons, mg. So let's use 10 for gravity. So since m is 1 and g is 10, the force is 10 newtons down towards the Earth. Now if I pull that 1 kilogram block significantly far away from the Earth, the gravitational field strength by the Earth is going to get smaller and smaller and smaller as we get away from that Earth. So will the force now be 10 newtons again? It won't. It's going to be something smaller. So let's just say 5 newtons in this case. So if I replace this 1 kilogram block with a 3 kilogram block, what do you think the force on the 3 kilogram block would be at this point right here? Right, it'd be 15. So the force on a 1 kilogram block is 5 newtons. So the force on a 3 kilogram block would be 15 newtons. This 5 newtons per kilogram is what we call our field strength. It is how much force is applied to each kilogram at that spot. Okay, so it's our gravitational field strength at that spot. What is the gravitational field strength at the Earth's surface? So how hard does the Earth pull on a 1 kilogram object? So it is 10 newtons, 10 newtons per kilogram, just like what we have down there. So what is the gravitational field strength at this point? We have the mass of the object and we have the force on the object. So take a moment and try to answer that. Good. It's 7 newtons per kilogram because each kilogram is being pulled with 7 newtons of force. Okay, so if we were to look at a picture of the Earth and look at the gravitational field strength of the Earth, you're going to have it very, very strong close to the Earth, and as we get away from the Earth, it's going to get weaker and weaker and weaker. Remember, force equals mg in this case, or W equals mg, but we're looking at the weight. And so in this case, g does not stay constant. G changes with how far we are away from the Earth, which is the case. We haven't ever done that in class yet because we've always been very close to the Earth, so g has always been constant. Okay, so the electric field has a very similar definition. Electric field, F for the electric field right here, is equal to QE. Electric field is the force that 1 coulomb of charge would feel if it were placed at this location. Q is not the charge that is causing the electric field. So the analogy would be for gravitational field strength, this would be M and this would be G, the acceleration due to gravity at that point. So for this Q right here, Q is the symbol for charge. And we call this the test charge. It's a charge that is feeling the force of the electric field. E is the electric field caused by other charges. Okay. So F is measured in newtons, Q, charge, is measured in coulombs, and E is measured in newtons per coulomb, or for each coulomb. So let's work out an example. At the location marked with an X, the electric field is 2,000 newtons per coulomb and points right. What is the electric force, size, and direction on a 6 times 10 to the negative 6 coulomb charge that is placed at the X? Okay, so why don't you try to work this out, and then I could work it out with you. Welcome back. So we have the X, we have an electric field pointing to the right, and we're given a test charge. In this case, our test charge positive will always be green for us. We'll stick with that. And negatives will be pink. So if the electric field is pointing to the right, the positive test charge will feel force to the right. So F equals QE, so we multiply them together, and you get 1.2 times 10 to the negative 2 newtons to the right. Okay, so that wasn't too bad. Let's try this again. Sometimes, so in this unit in electrostatics, we're going to be dealing with a lot of scientific notation. Sometimes some students are not comfortable with scientific notation, so just to show you, if we change these numbers to 20 and 3, it's just something very simple that you would feel very much more comfortable with. But since we're honors, we're going to get used to using scientific notation. Okay, so what if the charge were the same size but negative? So now we're going to have a negative charge. So remember, pinks will be negative for us. So how do you think this will change the problem? F equals QE, so E is still to the right, Q is still the same number, but the force will be in the opposite direction. Good. So same size force to the left, or same size force, but the force is now to the left. So what if the charge were placed somewhere else? We don't know. Who knows? We only know the electric field at this point. Whoops. Oops. We only know the electric field at this point right here. So we could only use F equals QE equation if the test charge and the electric field are at the same point. If they're not at the same point, who knows what the electric field is right here? So we can't answer that question right now. We can later with some more tools, but right now we cannot. Okay, so that is our introduction. We'll work out some more example problems in the next video.